In this video, we're going to look at some material that may seem familiar to you from past classes, the mean, the median, and the mode, but we're going to go quite a bit further than just those basic measurements. We are also in this video going to learn how to use our graphing calculators. So here we go. We're beginning to talk about measures of central tendency. In other words, the measures that we begin with are going to be ways of describing the center of a data set. And we've got to be careful about the word average because it can be rather ambiguous and it can really refer to either the mean, the median, or the mode. So I'm going to try to avoid the use of the word average as much as possible, and I would prefer to use the word mean whenever possible. Now, as we are looking at this chapter, there's different notations that we need to learn. And anytime we have a small letter N, it's going to refer to a sample size. And anytime we have a capital N, it's going to refer to a population size. And a couple of vocabulary words come into play here. And the first one is the word a statistic, and the second one is a parameter. A statistic is a characteristic or measure obtained by using a data value from a sample. Notice that sample starts with S and statistic starts with S. And parameter starts in P, and we use parameters to make predictions about population values. Okay, right now we will in this chapter be talking about the mean, X bar, which will be the notation, which we use to make predictions about a population parameter mu. That's the Greek letter M, which we pronounce mu. And a little bit later on in this section, we will use the letter S to represent a sample standard deviation, which we use to make predictions about the population standard deviation, which is another parameter values. We tend to use Greek letters whenever possible for the parameters. Now, the mean is something that you're very familiar with because in a lot of other math classes, you have been asked to calculate the mean. You basically add up the data values, you find the sum of the data values, and then you divide by the number of terms. Now, the text that I recently used, it says your text, but it's a recent text since you aren't using a book, says round your mean to one more decimal place than occurs in the raw data. In other words, if you're dealing with whole numbers such as 5, 6, 7, when you round your data, you find the mean, round it to the nearest tenth, go out to one decimal place. However, we will not go with that rule, and in our class, we will always take everything out to 4 decimal places, regardless of what any books may tell you. That'll be our general rule, unless I tell you otherwise. And I will specify on your test specifically how many decimal places do I want you to go. Now, I've just introduced to you this notation, which again we call X bar, and it says we add up our different X values. Now, the subscripts here stand for the first X value, the second X value, all the way up to the nth X value, divided by all N numbers. We add up those values. Now, when we use this funny little symbol here on the numerator, that is the Greek letter sigma, but it is the capital S, whereas over here, lowercase sigma is the lower s. And anytime we have sigma involved in a math equation, it refers to a sum. So it's a shorthand way of saying add up all the data values and divide by n. Okay? And we've already talked about the rounding rule, so I'm going to move on to the second measure of centrality, which is the mode. It is the data value that shows up the most. Notice that mode and most both start with MO. Okay, now a data set can be unimodal, meaning it has only one number that shows up the most. Bimodal, meaning it has two numbers that equally show up the most. Maybe a number shows up 5 times and then another number shows up 5 times. They would both share the title and that data set would be called bimodal. Or you can have multiple modes or no mode at all if every single data value just shows up once and no number shows up more frequently than any of the others. If one number shows up as the mode, if more than one number shows up the mode, we list each of them as part of our answer, and then otherwise we say no mode. So it's the value that shows up the most. Now that is being listed as a measure of center, but quite honestly, it isn't always the measure of center. The median is the middle value when the data values are listed in order. And if n is odd, if there are an odd number of data values, the median is the middle data values. But if n is even, the median is the mean or the average of the two middle values. For example, I have 5 fingers that I'm holding up here. I have a middle finger. We know which finger is in the middle. We know it's the 3rd out of 5 fingers. Now, if I happen to have 6 fingers, okay, I don't have a middle finger anymore. I have a middle 2, and I take the halfway point between those 2 fingers, so to speak. We're not talking about fingers here, but we're talking about a data set. So first off, let's start with a data set that I've given you there in the notes. And what you'll want to do first is put them in numerical order. If you list them in order, as I have done here, you can see that there are 12 values, and the median is the middle value. Now, you could say, hey, let's chop off from one end to another, but I notice there are 12, I notice there are 12 numbers in this data set, so I'm going to draw a line right between the first 6 and the second 6. I have an even number of data values. Therefore, and let me stretch this out a little bit. Therefore, I have 2 middle values and I have to take the mean of the middle 2. Since they're both in value, halfway between 12 and 12 is just 12. So we are going to leave that as 12 and say that the median is 12. Now the mode is the number that shows up the most, and in this data set, it just happens that the number 12 shows up 3 times. The next highest is 10 and 13, each of them showing up 2 times. But since the 12 shows up the most, it is the mode. Now to calculate the mean, I'm going to need to first add up the numbers and divide by n. If you add these up, you will find that they add up to 151, and then I will divide by 12, and that will give me, in a decimal form, rounded to 4 decimal places, because that will be the rule throughout this class, and this will be our answer, 12.5833. Okay, all 3 of these measures are purportedly ways of describing the center of a data set. Sometimes they are all in concert, as these 3 happen to be, but sometimes they don't always work as well, but they're all considered to be measures of center. Now, how do we handle grouped data? Let's say I've got these 6 different data values at the left, and they represent salaries, but the salary of $200 shows up 6 times. That's what the frequency means. And 300 shows up twice, 350 shows up twice, and each of the values 700, 840, and 950 each show up once. To find the mode, there's really no mathematical calculation. We can just see the one with the highest frequency of 6 is the $200. So $200 is the mode for that problem. As far as the median is concerned, I could list these out in order, but I don't want to write the number 200 6 times. 200, 200, 200, 200, 200, 200, then followed by a couple of 300s and a couple of 350s. What I would do is start chopping in from both ends. If I cut off 1, 2, 3, 4, 5, 6, one of those twos goes away, cross off all 6 of these 200s, and then my 7th value, the one in the middle, would be that 300, and I can just figure out the median that way. Now, there will be a way to do this on the calculator, and I'll mention that in a little bit. Now, as far as the mean goes, we know that we are to add up all of the data values and divide by the number of data values. So if I add these all up, I'm going to have 600 or 200 times 6, that would be 200 plus 200 plus 200 6 times, plus 300 added on twice, plus etc., going on through the numerator. And since there are 13 data values, I would be dividing by 13. If you do the grand total, add all those values up and divide by 13, we get $383.85. Now, this time I made the decision not to go out for data places or decimal places because we are dealing with money, and in money situations, we would rather take it out to the nearest cent, which means to take it 2 decimal places. Now, sometimes, as you see in this next problem, you don't have the raw data itself. Everything is grouped into classes. When that is the case, you use the class midpoint from each class. Now, for this first class, the class midpoint is going to be 100. And that's found, if you remember your definitions from chapter 2, by taking the lower class limit from this class. For example, this class really goes from 0 to 199, but we take the lower class limit from this class, the lower class limit from the next class, and we add them up and divide by 2, which just turns out to be 100. And when you do the same thing for the next class, halfway between 200 and 300 is, or 200 and 400 is 300, and likewise going down the whole list. Now, if we did need to do the calculation for the mean, which I'm not asking you to do, we'd have to go 100 plus 100 plus 100 plus 100 11 times, plus 85 of the 300s, plus 90 of the 500s, etc. So I'm not asking you to do the mean for this problem because, quite honestly, that's a little bit mean, pun intended, on this problem. Instead, we'll let the technology do this a little bit later for us. So it says, for the distribution above, what are the median and the modes? Well, the mode is pretty easy to see. That's the number that shows up the most, and we can see that the highest frequency is 135. So I'm going to say that the mode on this problem is going to be $900 using the class midpoint for that category or row. Now, what is the median? That's where I'd have to start chopping in from both ends. For example, if I take these first 3 rows, I notice they add up to 186. So I'm going to cross off 186 values from the bottom of the list. And when I cross off about 186 values from the top of the list, roughly I'm right around there. And you can tell that right here is where the middle of the data set is going to occur. And so the median will be $700 in this case. Now, we cannot get an actual raw answer out of this problem because all of the data was grouped together in classes. So that is the best we can do, and we use the class midpoint to represent those classes. We may be off a little bit if we had gone back to the original data, but it's pretty close. Continuing on, I want to talk a little bit about each of these measures. Now, I know you can read on your own, so I'm going to highlight some of these things. When you are dealing with the mean, You need to use all of the values of the data. Whereas in the median, you're starting to just chop off values from one end and the other. The mean varies less than the median or mode when samples are taken from a population and all three measures are computed. The mean varies less than the median because it's in the middle, basically. It doesn't vary at all because all the highs and the lows are being canceled out. The mean is used in computing other statistics such as the variance. We will talk about the variance a little bit later. The mean for a data set is unique and not necessarily one of these values. In other words, let's just talk about that one really quickly. If I have a data set and it only has two numbers in it, 6 and 7, and I want to find the mean of that data set, the mean is going to be 6.5. It's unique. It isn't one of the numbers in the set, and it doesn't need to be one of those numbers in the set. When you have a distribution or a category which is open-ended, you can't calculate a mean. Okay, for example, if we went back to that last problem and we had another category that basically had it being as 1400 and above, there really wouldn't be a way in that next category to find the class midpoint because there's no lower class limit of the next class after it. So in that sort of situation, the mean is not practical at all and you cannot calculate it. Now, the one I am most interested in is point number 6. The mean is affected by extremely high or low values, which we call outliers, and may not be the appropriate average to use when you do have these extremely large values. For example, you've got a whole bunch of numbers that are right around 6 and 7, and then I throw a 512 into the data set. Well, that number is going to really affect all these low numbers around 6 and 7, and the mean will be much higher. So it is very sensitive to these high and low numbers. The median is used when we must find the center of a data set. Okay, usually we use this whenever the data values fall into the upper half or the lower half of the distribution, and you're trying to find out, where do things fall relative to the center. The median is a good value also when you have problems dealing with income, problems dealing with house values, we tend to use the median. And the median is used for all open-ended distributions. If we have a large category that has that 1500 and above, well, that's where we start chopping off from both ends. And so it is an appropriate measure to use in this type of problem. And it is affected less than the mean by these extremely high and low values because these extremely high and low values are the ones that get cut off right off the bat at the beginning of your process. Now, the mode is used when you're trying to find the most typical case. It's the easiest to compute, as you know. The data will be used, the mode will be used when the data are nominal. Okay, you have category names when we're dealing with preferences such as gender and political opinion. We will not be using nominal data and qualitative data much in this class at all. And the mode is not always unique. We've talked about having a multimodal or bimodal data set. Now let's move on all the way over here to the right where I have a bell curve type of distribution drawn for you. How do you know which measure of central tendency you should use? Those key points that I've already talked about. The mean is very sensitive to the high and low values, but the median isn't because we start chopping off from both ends. It is true that the mode is not always near the center, but in this perfect case scenario, when you've got this bell curve or this symmetric distribution, this center bar that I have highlighted is special because it's the mean. You can tell by the symmetry that the highs and the lows are going to cancel each other out. It's the mode because you can tell it's the tallest bar, and it's the middle value also, the median of that data set. So all three are one and the same when you've got this perfectly shaped distribution. Now, down at the bottom here, you have what I consider to be a rather important graphic. In this perfect bell curve situation that you see in the center, we've got the mean and the median and the mode are all at the same place, at the same location. But what I'm trying to show you here is when you have a right skewed data set, you have some very large data values being added into the calculation. It pulls the mean toward that larger value. Okay, and in that case, the mean is going to be greater than the median. Likewise, if you have a very low value amongst a bunch of higher ones, that lower value is going to bring the mean down. I like to give the example of having a lot of mansions in Beverly Hills, and right between all these houses, you have a little 1 or 2 bedroom house mixed in with all these 11 and 15 bedroom homes. This house is going to be an extremely low value by comparison, and it's going to bring the mean should be lower for the whole neighborhood. And so when you have a left skewed or negatively skewed distribution, then the mean is going to be smaller than the median. Now, this would be one of those graphics that I would recommend you study prior to your next exam on this unit, because I will be asking you questions based upon these relationships down here at the bottom. Okay, now we're going to change gears, and we're not going to be looking at measures of center, but instead we're going to be looking at measures of variation. Now, the range is the easiest of these calculations here. It just measures the spread of the data. Essentially, you are just going to subtract the low value from the high value to get that range. So if you have a data set that starts at 17 and you've got a bunch of different numbers and it ends at the number 40, you would just subtract these low and high values and you'd say, the range is 23, because 40 minus 17 is 23. Now, the deviation measures, the standard deviation is going to be another one of those really important measures in this class, and it measures the variation in a data set by determining, and I'm going to say the missing parts here are how far the data values are from the mean on the average. Okay, I want you to have that definition down pat for yourself. Sorry I didn't have that typed up in advance. I accidentally left that one out. Now, the standard deviation, we're going to go through the calculations for that in a little bit, but let's talk about the variance. The variance is the square of the standard deviation. So basically, it would have the notation of S squared or sigma squared. Now, we're not going to be dealing with the variance much at all in this class, because I don't really find the usefulness of dealing with squared units. If I asked you, what was the average test score for a class? You'd say, it was 30, and that makes sense, 30 points. But when you start talking about squared points, how far was a value away from a mean? I was 25 squared points away. That just doesn't make much sense as, in terms of the way our brains operate. So we will not be talking about the variance. It is used, however, quite a bit in psychological studies, and it will be a measure that you might use in some of your future classes, but we will not be using the variance very much at all. Okay, basically, we're looking at how far are the data values spread out. And if you have data values that are spread out very far, we say that the standard deviation and the variance are larger. But if all of your values are closer together, we tend to say that the standard deviation is smaller, and therefore the variance will be smaller. Now, we mentioned that there are two different standard deviations. the left here, using the Greek, is the population standard deviation. And then we've got the sample standard deviation using the letter S. And these formulas are very similar to each other. They both have a square root of the sum of how far data values are away from the mean, etc. And let me just begin with showing you how you will do this calculation manually. This will not be something that you will need to do at all, because we're going to be bringing out the calculators in a little bit, and the calculators will make this a very easy calculation. It's basically done for you. So I've got a very simple data set. It's got the numbers 1, 2, 6, and 7 in it, and I've listed it down the first column here. And the first thing I'm going to be asking is, how far are each of these X values away from the mean? So over here at the right, I've got it covered up, but the mean of this data set is found by adding all these values up and dividing by 4. Now, if you add these up, we get 16 on the numerator divided by 4, and it turns out the mean is 4. So really, I'm asking, how far are these values away from 4? So in the first case at the top, I'm going to go 1 minus 4 and get -3. And then I'll move to the next row. 2 minus 4 is -2. 6 minus 4 is +2. And 7 minus 4 is 3. Now the next row says, take these differences that we just found in the previous column and square them. So -3 is going to square to 9. And then the remaining values will square to 4, 4, and 9 respectively. And then what we do is we have to add all those numbers up in that second column, which says it's going to add up to 26. Now let's go with the population standard deviation formula. I'm going to take this formula and say, okay, I'm going to have the square root, sigma is going to equal the square root of the sum of x minus mu squared. That's the sum that I just found there, 26. Which I'm going to divide by n. Well, I had 4 data values, so I'm going to divide that by 4, and that will give me the square root of 6.5, because 26 divided by 4 is 6.5. And if you take your calculator and you say, I want to find the square root of 6.5, which I'm doing right now, you're going to end up getting 2.5495. Now, that is a lot of work, and I made it simple because we only had 4 data values. Can you imagine having a data set with 175 values in it, having to calculate the mean, asking how far each of those were away from the mean, squaring all those values, adding them up and dividing by n? Wow, that would be quite a bit of a challenge. And that's in the past why statistics as a class has had such a bad rap. Now that we've got technology that will do this for you, it just makes life so much nicer. And it gives us the freedom to move on and really focus our attention on other things. Now that was the formula for the population standard deviation. The sample standard deviation is basically the same thing. I've traded out mu for x bar. That's because we might not have a population mean, we just have a sample mean to deal with. And then n minus 1 is what we divide by. So the formula is exactly the same thing, but for us, we would, on this problem, we would be saying, okay, S is going to equal the square root of 26 over 3. And so I'd have to go 26 divided by 3 on my calculator, which gives me 8.666667. And then I would have to take the square root of that answer. And it turns out the value is going to be, and I just did this quickly on my calculator, 2.9439. Notice how my sample standard deviation is larger than my population standard deviation. That will always be the case. You can, on any problem that we do, break out your calculator and you will always see that the sample standard deviation is larger. Now you may ask, well, why are we dividing by n-1? Why did we come up with that? Well, that's an answer that really isn't part of this course. I hate to push you down the road and say, okay, you'll get that in a future math class, but that's really the answer here. But I can tell you that when you are using samples to make predictions about a population, you usually want to pad your samples a little bit because you want to make more accurate predictions. By having a larger sample standard deviation, it allows us to pad the numbers, simply put, to help us with that estimation. Why are we padding it with an n-1? I'm not really going to be able to answer that in the scope of this course, okay? Let's move on here. And now it's time to start talking about our calculator. And I've got a lot of things here on your screen, which I'm going to let you read on your own. For this class, we are always going to, well, I'm going to be focusing on the Texas Instrument models. And I'm going to open up my calculator here, and this is the starting point on my screen. And I'm just going to give you a little bit of an introduction to the calculator, and you will get to know this calculator very well. Now, I am using the Texas Instruments TI 84 plus CE. The plus CE stands for color edition, not something that's mandated. If you are using another calculator, proceed at your own risk. You're going to have to learn how to do those different features on your own. But for us, I like to call this the main screen. This is where you can do some calculations, such as 89 minus 65. You don't have an equal button, so you hit the enter button down in the bottom corner, the one that just turned red on the screen. That's like your equal sign. Now, what's nice here is if you want to subtract something from 24, you just hit minus, and it brings the answer that you had to your previous problem down. It then says minus, and you can type in the 17 that you want to subtract. It's great when you're balancing your checkbook because you can see just what you typed in and make sure that you didn't make any mistakes. So this is your main screen, and we're going to learn I know it can be overwhelming, but we will, as we need them, start using some of the keys that we need at different times. You also have a y equals screen. I'm going to clear off a couple of these lines here, but this is where you would be doing the graphing. Again, my y equals button is up at the top left corner of the screen. We will get into this screen more so for the graphing of lines in chapter 11 when we start doing linear regression. But we also have the ability up in the top where it says plot. If I hit second and then above that y equals button, you can see the word stat plot. That allows me to turn on the different plot features of the calculator. We will be doing that a little bit later also. Anytime you want to quit out of there, I'm going to say second and then quit, which is above the mode button. And that will take you back to what you might call your home screen. Anytime you want to just kind of clear off your screen, you have a clear button over here around 3 o'clock on the keyboard, so to speak. Now let's go into that mode button. If you hit the mode button, depending upon the model of calculator you have, you may have a lot of different choices. Essentially, you want the entire first column highlighted for yourself, except if you have a model of a calculator down here that has a stat diagnostics. You want your diagnostics turned on, and if you have a stat wizard button on the next line, you would like to have that turned on also. I don't ever bother with setting the clock because you never need the clock on these calculators. Again, I'm going to hit second quit to get out of there. One little thing I want to mention is sometimes your calculator may give you the wrong answer, but it's not the calculator's fault. It might be your fault. Okay, so let me switch back really quickly to this blue screen here, and let's pretend I wanted to do the following calculation. 10 plus 14 divided by 4. Now you know that 10 plus 14 is 24, and divided by 4, we should get an answer of 6. What I didn't mention here is there's an implied parentheses around the numerator, which says, hey, add the numerator first before you do the division. So we have 10 plus 14 divided by 4. Now, when I go back to my calculator, if I write 10 plus 14 and then hit divide by 4 and hit enter, it's not going to give me an answer of 6. It's giving me 13.5 because the calculator does order of operations. It's thinking that 14 divided by 4 is 3.5, and then we're adding that 3.5 to the 10. So there are two ways to remedy this situation. You can either use your parentheses keys, open parentheses, 10 plus 14, close parentheses, then hit divide by 4 and get the correct answer of 6 that way. Or you can do the numerator separately, 10 plus 14. When you hit enter, you get the numerator, then you take that numerator and divide by 4 as a second step, and it will take you to the 6. Whenever you hit enter, what basically happens is you are stopping the order of operations on your calculator, which allows you to do the numerator on its own and then divide by the 6. This is a common little area of errors. Second off, I want to mention the minus sign. You have a minus sign over here in the far right column, but you also have a negative sign on the bottom row just to the left of the enter button. Now, in your algebra classes, a minus and subtraction really are the same thing, but on our calculator, they aren't. We will almost never be using this negative button, and we will almost always be just using the minus button. But when we do get to those type of problems, I will specify for you. Now, I can't really do a calculation here without an error, so I'm going to hit clear once to clear the line, clear a second time to clear the screen. Okay, what you need to do next is learn how to use the statistical entry keys. Now, what you have in your notes is a data set that I've got typed in there, beginning with the number 42, and I'm going to do these same values with you. So I'm going to hit my stat button. Anytime you start a problem, you basically always start with stat. You then click edit, which will now give us a list of numbers. Now I've got some stuff in here from a previous problem. So I'm going to go up to the top of the row. I'm moving my up arrow key to the top, and I'm going to hit clear, because whenever I do something in the top of a list, it applies to everything in that whole list. When I hit enter, that whole list is cleared out. So I'm now going to type in the numbers 42, followed by 52, 53, 55, 66, 68. And recall that you can pause this video at any time and make little notes for yourself, but those are my data values that I've just entered in. Anytime you want to find some statistical values based upon the numbers that you have typed into a list, you are then going to hit the stat button. When you hit the stat button, you move one column over to the right to calculate, and we will be doing one variable statistics. We will never be doing two variable statistics, just the one variable statistics. I can either choose the button 1 to choose one on the menu, or I can hit my enter button to go into the one that's highlighted there, which is the number 1. When I hit enter, it's going to ask me what list do I want to do. Now, to get my list 1 through 6 access, notice they're above the keys I want in blue. I'm going to hit second 1, which accesses the L1. I'm not going to deal with a frequency list right now. And I'm just going to move down to calculate. Now, do not spell it list 1 with an L and then a 1. We will not be using these green button keys or the green ones with the alpha key at all in this class. If you want L1, you're going to go second the number 1, and that's where the L1 shows up on your calculator. Now, when you hit calculate, it's going to give us a bunch of different values. Okay, it tells me right at the very top here what the mean is. It tells me if I added up all the values, that sigma says add up all the values, it adds up to 336. The sigma x squared says add the squares together. That would be 42 squared plus 52 squared plus 53 squared, etc., adding up the square of each of the data values you've entered. Then we have our sample and population standard deviations. Notice instead of S, they use S subscript X and sigma subscript X. That was just a decision that Texas Instruments decided to do. And we will, well, first off, notice how the sample standard deviation is larger than the population standard deviation. I told you that would always be the case. And we will always be rounding to 4 decimal places. So for us, the sample standard deviation would be 9.650. And we'd stop at the 0 because the digit after it is a 1, which says round down, which means ignore the 1 and everything after it. For the population standard deviation, it will be 8.8129. And the reason I'm not reading the 8 here is after my cursor here on the screen, after that 8, you have a 6. 5 and above says round up, which means add 1 to the 8 and make that 8.8129. I just wanted to give you that little bit of a refresher on rounding, because that is a key skill in this class, as throughout this class, we are going to be using decimal numbers. The N says, oh, we entered 6 data values in. And notice you've got an arrow down here. That arrow says there's more to the screen. If I hit my down arrow a few times, it's going to fill out the rest here. It tells me my minimum value is 42. This Q1 thing, that's the first quartile. We'll talk about that towards the end of this chapter. The median, you know about that. Q3, the third quartile. And the maximum number, the largest number you entered was 68. So with just a few keystrokes, you get all of this numerical information, and it's much faster than doing things by hand. So again, you are going to hit your stat button, hit edit, and that allows you to enter the numbers into your list. If you ever want to clear out your list, you go to the top of the list, you hit clear, followed by enter, and that will clear out the list. Don't hit delete, because if you hit delete, the whole list is gone. And if you try and find your list 1, it seems to be gone. If you ever do that, don't worry. You hit your stat button, you go down here to choice 5, hit setup editor, hit enter, and that just will automatically give you your list 1 through 6 back. If I hit stat, you'll notice that list 1 is back again. So it's just, that's just something to tuck away in your memory, because we don't delete very often. Just pretend that delete button isn't there, and just always use the clear button to clear off a row or a screen or a number, and use the second quit to get out of a screen that you want to get out of. And by the way, beneath, you have an on button down at the bottom left corner. You have to hit the blue second button before the word off, which is above the word on, in order to turn your calculator off. And when you do turn your calculator off, all of the values that are in your lists remain there, and you don't have to worry, they'll still be there the next time you turn your calculator on. Okay, now let's go back to my blue screen and let's turn a little bit in your notes. And the first thing we want to do is we want to find the mean and standard deviations of this data set. Now, this data set here is not the one I just used. So I need to go back into our calculator, which I'm going to do right now with you. You have the notes in front of you, so you know what to enter in. And I'm going to go to the top of my list. I'm going to hit clear and then enter. And then we're going to type these numbers in. 64, I'm going to hit enter to move to the next row. 66, 66 again, 68, 69, 70, 72, and 73. Let me make a note to you, okay? First off, it is worth the extra half a second to glance at your paper, then glance at your screen between every single data entry, because if you type one number in incorrectly, it messes up that entire problem. And so you will have to learn to make sure you check it extra carefully. And if you have any dyslexia, it's even more important for you that you are very slowly entering the data values in. After you do that, again, we hit our stat button, we go over to calculate, we hit one variable statistics, our data is in list 1, we scroll down to calculate, we hit enter, and out come all these numbers. So I'm going to quit out of here for a moment, and I'm going to go back to my blue screen. And I've already got those data values listed up here on the top of my screen. And what I'm going to do now is round these to 4 places. Now, for X bar, the mean, the sample mean, it doesn't need to be rounded. It is 68.5. We will never in this class access the sum of the data, nor will we deal with the sum of the squares. You can pretend those aren't there. Now, in some of your other classes, you may do this. And when I used to teach this class 25 years ago, we were using those 2 values in a major way. But these calculators have graduated to a point now where we don't need those values any longer. Now, the sample standard deviation rounded to 4 places is 3.1168. And the population standard deviation is the 2.9155. Notice I've rounded up in both of these two to that 4th digit out, and having that as a general rule, going to 4 decimal place accuracy. Now, if we go back to page 14 in your notes, we did a problem where we used the class midpoint to represent the rows where you did not have specific values. You had ranges instead. And for example, we went from 0 to 200 we took the halfway between the lower class limits to get the 100. Etc. Now, if you want to find the median of all the different calculations for this data set, what you're going to do is you're going to go into one var stats and use L1 and L2. Now, let me show you how we're going to do that on our calculator. And again, it's going to take me a moment to type these values in, but what do we have but time to learn these calculators? So here we go. I'm going into my calculator and I want to get rid of this first column. So I'm going up to the top, I'm hitting clear and enter. Now this first column is pretty easy to type in. It's just 100, 300, 500, 700, 900, 1,100, 1,003, 1,000, let me do that back a space, 300, and that's it for the first column. Then my next column is going to be 11, 85, 90, 115, 138, 37, and 22. So this time the frequencies are going in my second list. Anytime the second list contains frequencies, we do something a little bit different. We hit our stat button, we go over to calc. It's still going to be one variable statistics, the first choice, but this time we tell it specifically that our frequency list is going to be list 2. So I'm going to hit second L2 there. And when I hit second L2 and hit enter, now I've got a screen full of data here. Now I'm going to very quickly take a snapshot of that screen and bring this back over to our other page here, because we're going to access it and control paste. Here we go with these values. Now you'll notice that what you have on your calculator screen has all these values. Notice the value of n is 498. That's what that first column adds up to. Okay, there's no way we wanted to type in almost 500 numbers. Now I've got listed here one variable statistics L1, L2. Some of you who have an older calculator, and when you go to hit one variable statistics, you don't get that nice menu screen like I have. You just have a blinking cursor that says 1 bar stats. Well, in that case, you're just going to type in L1 and then find your comma key, which is above the number 7, and then L2. And then you will get to this output screen that I'm showing you right here. So for this problem, the mean is going to be that, whoa, I've got a different number here than I had on my screen. Perhaps I had a typo. So, I'm going to go back and check my data really quick and see if I had a typo. Notice how I've got to be very careful. Either I had a typo or I have the wrong answer here in my notes. So I'm going to go back right now and look at my data. And I've got my 100, 300, 500, 700, 900, 1100, 1300, 11, 85, 90, 115, 100. Yep, you see it? There's that 138, which should be 135. And so I was working too quickly. Part of me says, oh no, I'm going to go and redo this whole video. But another part of me says, hey, this is how we learn. And I'm just showing you by example how important it is for us to go through and double check our numbers as we're typing them in. Stat, go over to calculate, one variable statistics, keep my list 1 and list 2 here, hit calculate. Now I want a screenshot of this. There we go. I'm going to copy it and we're going to head back to our other screen. And I know some of you were probably a moment ago going, whoa, you've got a mistake, you've got a mistake, haha, you got a mistake. But here we go, we've caught it, and that's good news. And so here is what we've got, and I'm just going to leave that right there for you. And now my means with that 692 point, and I think I've got another typo in here. This should be 7273. So that should be not a 2 here, but it should be a 7. So you can imagine how much prepping had to go into this lecture. So please be forgiving for one little mistake here. And then when we move on to our sample standard deviation, 285.8818, that is a match. And my population standard deviation ending in 5928, That matches perfectly also. So you can see that you have to be careful when you are typing these numbers in, because one little typo can mess up the whole calculation. So I think lesson is learned here. Okay, some notation up here, which is now old business to us, but it's summarized for you. We have a row of sample values and a row of population values, and we have different notations for each of the different situations. So sample size, it's lowercase n versus capital N, sample mean versus population mean, and then we have sample standard deviation versus population standard deviation. We will talk more about the population mean in a little bit. And I've got a couple notes here about the variation and the standard deviation. I'll let you read those ones on your own because they're pretty straightforward. Here we go. Now a little bit about this notation. When you are finding the mean of a data set, we can either consider the mean to be a sample mean, x bar, or a population mean, mu, depending on how the value is being interpreted. So if I have this data set with 11 numbers in it, and I am trying to find the mean, if we're interested in this team only, they would be our population, and we would use the mu notation of that value 78.2, and we'd say our population size is 11 because they are our population. If this team were a sample of all the NBA teams, then it would be a sample mean, and we use the x bar notation with a lowercase n for n equals 11. So now I've got an exercise for you to practice with. I've got a bunch of data values up there, and I want you to please find the mean and the standard deviation. And this would be a good time to pause your recording. And I'm going to say welcome back, assuming you paused the recording. And this is a great place to check your math, that you do indeed get these values. Check your rounding also. And I'm going to assume that you guys did pretty well on it. This is a basic skill that you really do want to master in this class. Continuing on, now I'm going to deal with two different data sets. And I'm going to begin by asking which data set appears to have more deviation. Well, when I look through the numbers, the first data set seems to have a high value of 30 and 28, and the low value looks like it's the 9. But the second data set goes all the way up to 56, and it goes all the way down to 3. So it appears that data set 2 has more deviation. It appears to be more spread out. Now, I'm going to save you some time here. I've already calculated the mean and standard deviation of each data set, and I use the sample standard deviation. And it turns out that both data sets have the same mean. It's 20. And then when I go look at the sample standard deviations, we get 5.9 and 14.7 respectively. And this time I've just rounded to 1 decimal place. I know normally I would go 4 places out, but I'm about to do something where I don't want that level of accuracy. But we had said that the second data set appears to be more deviant, having a larger deviation, and that actually is the case when you compare these values of S. Okay. Now, part D is a little bit interesting. It's a different type of problem, and there's interesting vocabulary in it, and you will have a homework problem that's very similar to part D. I've got that same set of data, and what I've done is I have plotted that first data set, but I started by putting my mean right down the center was 20 for both data sets. That's why you see this bar going straight down the center, and you can see that that's an X bar down below. And then what I did in that first data set is I went tick, tick, tick to the right, tick, tick, tick to the left. And what I did is I added 5.9. So I started at 20, I added 5.9 to get to 25.9. I added another 5.9 to get to 31.8. I added another 5.9 to get, well, I didn't, but it would have been what I would have added. And then I started at 20 and I subtracted 5.9 over and over again to create this scaling. And then I actually went into that data set and I said, okay, let's plot those dots. For example, our smallest number in that first data set was 9. This dot right here that I'm moving around was just to the right of that 8.2. And the largest number in that data set was 30. So this is my dot that I use to represent the 30, just to the left of the 31.8. And you can see how spread out the data values are. Now, what are we saying? I'm looking at this and I see that all of the data, all those green dots, lie within 2 standard deviations to either side of the mean. Okay, that's vocabulary I want you to get. Within 2 standard deviations to either side, left or right of the mean. In other words, if I were to draw these brackets in here and say there's 2 standard deviations to the left and 2 standard deviations to the right, all those data values fall within 2 standard deviations to either side of the mean. Now, the second data set had a much larger standard deviation, and I wanted to line these 2 data sets up. So what I did is I added 14.7. I started at the center and I added 14.7. I added 14.7 again and then again. And then likewise, I went down 14.7 repeatedly. And in blue, you can see I wrote the 0, 1, 2, 3. 0 is center. I went 1, 2, and 3 standard deviations to the right, 1, 2, and 3 to the left. And when I went to the left, I gave them negative values there. And then what I did to illustrate the deviation was I drew in all the dots for the second data set. And based on that second data set, do they all lie within 2 standard deviations? Well, these are 2 different types of deviations, but for the second data set, wow, 2 deviations goes all the way down to negative 9.4 and all the way up to 49.4. And yeah, all the data values again lie within 2 standard deviations. So what I'm trying to do is show you a way with this new vocabulary to represent the spread of a data set. And almost all the time, almost all your data is going to lie within 2 or 3 standard deviations to either side of the mean. Continuing on, we have something called Chebyshev's theorem. Okay, and Chebyshev's theorem is a way of trying to talk about what percentage of data will fall within a certain number of standard deviations to either side of the mean. Now, what's nice about Chebyshev's theorem is it does not require a bell curve. You can have any old data set that's got any old distribution, and I like to say that the curve can be wonky, for lack of a better word. Okay, you don't have to have, it doesn't deal with any type of special curve. We could actually have a data set that looks like this, that says, a lot of data on the left, it goes up, it does this, and then it's like almost dead for a while, and then it goes up like that. And maybe that's our distribution instead. And that is not a bell curve. So that's when we use Chebyshev's theorem. And what I've done is I've created this table for you, and it doesn't tell us much about 0. If we plug in 1 over 0 squared, That basically is undefined. We know in mathematics, whenever we divide by 0, we get undefined. So that really doesn't help much. When I get 1 over 1 squared, that's just equal to 1, and I get 1 minus that 1, and I get 0, and there's really no claim here at all. But when I go 1 over 2 squared, and I let the value 2 be substituted in, that gives me 1/4. If you go to this formula, 1 minus that value of 1/4, then I get 3/4. Now 3/4 as a decimal is 0.75. So I'm going to say at least 75% of the data values will fall within 2 standard deviations to either side of the mean, no matter how wonky the data set looks, okay? And if we go 3 standard deviations out, my formula would give me 1 over 3 squared. That becomes 1 over 9. And when I go 1 minus 1/9, I get 8 over 9. Now 8 over 9 is going to turn into at least, and it becomes 88 point repeating 8% of the data. So if you go 3 standard deviations out to either side of the mean, regardless of the data set, you're going to get almost 90% of the data falling within 3 of those standard deviations, just like I showed you on the previous screen. Now, we did a lot better on this previous screen, but it says if I go 3 to the left and 3 to the right, I'm going to have at least 88.888% of the data. Well, we actually ended up getting all the data in both of these problems. All of them fell within 2 standard deviations, but there weren't any major deviating values in this problem. But this is what we apply to what I'm going to call wonky data sets, when you don't have a nice, neat bell curve. This is just a side topic in this course. It is in this chapter only, and after this chapter, we will not come back to this theorem at all. Continuing on, this is a different way of looking at things. If we have not a wonky curve, but a nice, neat bell curve that we see over here on the right, okay, or what's known as a normal curve, then we can apply what's called the empirical rule. Sometimes it's called the 68, 95, 99.7 rule. And basically it says about 68% of the data will fall within 1 standard deviation. If you go back to that chart from the previous problem, when we dealt with 1 standard deviation, there was no claim at all, okay? Now, when we go 2 standard deviations, it's going to tell us we're going to get about 95% of the data, and we've got a much stronger claim. About 99.7% of the data values will fall within 3 standard deviations to either side of the mean when the data is normally distributed. Now, Chebyshev's theorem applies to any distribution, regardless of the shape. For this theorem, you do need to have this normal bell curve. Okay, so we say that in any data set, almost all the data will lie within 3 standard deviations to either side of the mean. And we say X bar plus 3 standard deviations or X bar minus 3 standard deviations. The mean plus or minus 3 standard deviations. Now over at the right, instead of just going 68, 95, 99.7, what I've done is I've taken the 68 and by symmetry, I've broken it down so you can see 34 on each side. And then if you find out how much is left, if you subtract the 90 minus the 68, that's the green and the purple together minus the purple, you get the green, which is 27%. If you split that 27 in half, you get 13.5 in each of those 2 green sections. And likewise, you get about 2.35% in those orange sections. So that's kind of a neat little graphic to help you break those percentages down. And we will be using that graphic with the purple, green, and orange in it quite a bit. Okay, let's give you an example problem. And I'm sorry this video is running so long, but I wanted to just make one big video for the first half of this chapter to really get these ideas out there without having any exit points, because if you close down the video, odds are you're not going to come back in again. So I just wanted to get it all out there in one big push. So here we go. This example, the average farm in the United States in 2004 contained 443 acres with a standard deviation of 42 acres. Using Chebyshev's theorem, meaning we don't know if it's bell curve or not, find the minimum percentage of data values that will fall in the range from 338 to 548 acres. Okay. When I have a mean and a standard deviation type of problem, I always begin with a number line sketch. So I began by drawing a number line. In green, I drew in the center 443 where the mean is. And then I took my standard deviation of 42 and I went add 42, add 42, add 42 to move to the right, and subtract, subtract, subtract 42 each time to go to the left. Those are my X values. Those are the actual values themselves. Then I have these Z values, which are referring to the number of standard deviations above or below with these 1s, 2s, and 3s that I have labeled. So that's the basic picture to begin this problem. And then they wanted to know what is the minimum percentage that will fall within 338 to 548. And you can see those purple dots that I've drawn there. And it turns out that those are 2.5 standard deviations to either side of the mean. So I can show it to you with this picture. I went 42, 42, and then whoops, 21 more. That's half of the 42. So that's 2.5 standard deviations to the right. And it turns out that it's 2.5 standard deviations to the left. Now, Chebyshev's theorem can be applied, which is 1 minus 1 over, and there's that 2.5 I substituted in, squared, which gives me 0.84. And that tells me my answer will be at least 84% will fall between these two numbers. And I understand, I went through that really quick. You might just want to pause this and stare at that screen there, and hopefully it will make sense. If not, rewind it, play it again, because if you leave now and say, oh, I'll come back and watch it later, you probably won't. So let's make sure you pause it and make sense out of it. The next question says, in a distribution of 160 values with a mean of 72, at least 120 are within this interval from 66 to 77. Stop there. That's all I need to draw a picture. So I drew myself a picture here, and I said 72 was in the center. And I knew I went from 67 to 77, which is 5 down and 5 up. At this point, I don't know about how many standard deviations that was. I don't know about that -2 and +2. But I do have a clue that at least 120 of the 160. Now, this one's a little bit more challenging. I'm going to tell you that 120 is 75% of 160. It's 3/4 of it. And then I know that 75% corresponds to 2 standard deviations. How do I know that? If I go back to the table a couple screens back, notice at least 75% right there goes with the 2 standard deviations. So that's what I did, and that allowed me to go -2 and +2 right up there on my number line. So I'm going to say that the interval from 67 to 77 is centered at 72. So that's all from the first sentence. That's what I was able to glean out of it. Now I'm going to move in, and I've got to go a little bit further. Approximately what percentage of values should be in the interval from 62 to 82? Well, that's going to go out a little bit further to the left and to the right. So I took my number line picture and I went to 62 and 82. Well, that's where they are in the picture, and you can just tell that that's going to refer to 4 standard deviations. Look at the scaling I have across the bottom, and that tells you what's going on there. Now that I have 4 standard deviations, and since I know I'm dealing with Chebyshev's theorem, then I'm going to do the following. 1 minus 1 over 4 squared. There's my input of 4. Gives me 1/16. Okay, 1 minus that 16th gives me 15/16, and there's my decimal version of it. So I'm going to write the phrase at least 93.75% will be within that interval from 62 to 82. I probably should have had a 1 run right in there just for completeness. That's a 1 minus. Okay, moving on to problem number 3. Continuing on with these practice problems. Problem number 3. The average full-time faculty member in a post-secondary degree-granting institution works an average of 53 hours per week. Okay, I wish I could cut back to 53 hours a week. I drew a picture and I had 53 in the middle. And then it says, if we assume the standard deviation is 2.8 hours, okay, you can see that I added 2.8s 3 times to the right and 3 times to the left. What percentage of faculty work more than 58.6 hours per week? Okay, there's my 58.6 right there. And it's 2 standard deviations to the right. That's the first thing that catches my attention. That's probably what I have listed here. Well, I went straight to the calculation. I noticed it was 2 standard deviations. I went 1 minus 1 over 2 squared, got my 3/4, and we know that that means at least 75% are going to be within 2 standard deviation. Okay, now, what do I have underneath my cover here? It didn't say that was within 2 standard deviations. Now, I don't want to know what's within 2 standard deviations. I want to know what's in that pink area because it said works more than 58.6. I need what's there. So if I have at least 75% in there, then I've got at most 25% split between the left side and the right side. So by symmetry, I said, okay, I've got at least 75% in the middle. That means there's at most 25%. That's an upper boundary for the left and the right. And if I'm cutting that in half, I'm going to have a 12.5% for that right tail. So I'm going to say at most 25% are beyond the 2 standard deviations. That's the left and the right combined. So my answer is, cutting that in half, at most 12.5% work more than 58.6 hours. Whew. That's a lot of work on this problem. And hopefully you were able to follow my logic through. If not, you might want to pause the video again and go back and rewind it. Now, part B changes the game. It looks like almost the same exact problem, but now what's happened is they have changed this and it says if it's a bell curve distribution. Okay, no longer are we in the Chebyshev's theorem problem. This one says, we know with a bell curve with 2 standard deviations, we know that that's about 95%. So 95% is in the middle, and that means there's 5% left over for the 2 tails on the left and the right. So one of those tails is going to be 2.5%, and that's why 2.5% is my answer on that problem. So a little bit different using the same exact logic. Or I guess you could actually take my logic right here and say, not only, here I have 2.35%, but I have 95 total between these 2 bars. which means there's 5% left over. 2.5% on the left and 2.5% over on the right. Now the reason it doesn't match up is there's more area that's very tiny off to the right and left of these orange sections. That's the difference between those, the value of 2.5 that I gave and the 2.35 that you see on the table there. Okay, one last problem and we'll finish off. Whoop, I guess that's it for this video. So we're going to stop right there and then we'll start in on the rest of it in a next video. Okay, let me stop the recording and we'll see you back next time.